Hello everybody, welcome back to our next screencast lecture. Today's topic is continuing the theme of earthquakes. So this time we're going to focus on how do scientists find the location of the epicenter. To be able to fully understand this, let's do a little bit of quick review. The first thing we need to be reminded of is that the origin of the earthquake is known as the focus. In addition, the focus is located underground and you would find it on a fault. So that's really the big problem. The big problem is that since the focus is located deep under the Earth's surface, how do scientists figure out where the earthquake started? Well, let's take a look at the procedure that you can use, and you will get to try in class activities. All right, here's some data from an actual seismogram station. What happened was an earthquake primary wave was recorded, and as soon as that wave is recorded, a timer starts counting. So the primary wave arrives, and then some period of time goes by, and then the S wave hits. Now, in this case, the S wave hit 200 seconds after the primary wave arrived. And then there was a little bit more time, another probably about 300 seconds, and then the surface wave arrives. Knowing this information, this will help to determine how far away the epicenter is located. Okay, this might help you to understand this situation. Let's imagine that you are at a seismograph station, you're working at a seismograph station, and you record two completely separate earthquakes. Now, how can you figure out which one is further away from you? Okay, the first earthquake, scenario A, the P wave arrived at 10 a.m. Then the S wave arrived 15 minutes later. For earthquake B, the P wave arrived at 10 a.m. Same time, different day, but the S wave arrived 8 minutes later. At which scenario is this seismogram station closer to the epicenter of the earthquake? Was it closer to the first earthquake, or was it closer to the second earthquake? Well, it's definitely closer to the second earthquake because the difference in arrival times is smaller, so the station must be closer. Here, the earthquake, the secondary wave arrived 8 minutes later, and this one, the secondary wave arrived 15 minutes later. Now let's take a look at this chart in the next slide. This chart shows that as you get further away from an earthquake's epicenter, the time difference between the P wave and the S wave is going to increase. So if you're really super close to the epicenter, if you're really close to that focus, you're going to have the P wave arrive, and then moments later the S wave will arrive. It's going to be very, very close, not very big a time in between the two. And as you get further and further away, that time differential is going to increase. So maybe the primary wave hits, and then you're sitting around, then the S wave hits, the secondary wave hits, and you know that you are located further and further away from the focus. This data of the time differential has been combined onto a pretty easy to use chart. I like this chart. The way you use this is, let's say that let's look at that second example where at 10 a.m. the primary wave comes, and 8 minutes later the secondary wave hits. So what you would do is the time differential is 8 minutes, so you go to here to 8 minutes, and then you would go across to here, and you see that the distance from the epicenter is about 6,200 kilometers. To locate the epicenter, you're going to need data from at least 3 different seismograph stations. Now let's walk through this, and I'll show you how this is done. You are going to need data from 3 different seismograph stations. The first seismograph station in this case we're going to use is Indianapolis, Indiana. So that's right here. And you're sitting in that station in Indianapolis, and you feel the P wave hit, and then the clock starts. 50 seconds later, the secondary wave arrives. So you look at this chart. Here's 1 minute, so 50 seconds is about here. That comes across, and you're going to see it hits the line here. We go down here. It's halfway between 0 and 1,000 kilometers, so that is approximately 500 kilometers away. So we know that the earthquake's focus is somewhere 500 kilometers away from Indianapolis. So you're going to now use this chart right here, the scale in kilometers. It's going to be, this line represents the distance of 500 kilometers. Focus could be located 500 kilometers from Indianapolis, so it could potentially be here. Is there any other place that could be 500 kilometers away from Indianapolis? Well, sure, over here could be. So that'd be somewhere in Missouri. It could be up here, somewhere in Michigan, or it could be down here, somewhere in Tennessee. Now, what's a better way to do this instead of drawing an infinite number of lines away from Indianapolis? A good way to do that is to draw a circle. So if you take your circle, your compass circle, and you put it on the scale here from 0 to 500, and then we can take our compass and draw a circle, and then we can determine that the focus of this earthquake could be anywhere on this circle. Second station, Oklahoma City. The S wave arrives 2 minutes, 15 seconds after the P wave. How far away is the epicenter? Here, find 2 minutes. 2 minutes, 15 seconds is here. We go across, we hit the line here, come back down here, and the distance is 1,500 kilometers. So again, where could the focus be located on this map if the earthquake is 1,500 kilometers away from Oklahoma City? We're just going to do the exact same thing. So take our compass circle and make a circle that represents 1,500 kilometers, put it around Oklahoma City, and we see that the focus of this earthquake has to be either here or here. So we got it narrowed down to 2 points. And then finally, we're going to use Charlotte. Here's Charlotte. And Charlotte's S wave arrives 1.5 minutes after the P wave. How far away is the epicenter? Here's 1.5 minutes. Go across here, this line, down to here. And we see that the distance is about 900 kilometers. Make our circle. 900 kilometers is going to be here. And we draw that circle. And now we have from Indianapolis, it's this far away. From Oklahoma City, it's going to be this far away. From Charlotte, it's going to be this far away. The only place where all three of them meet is right here at that location. So now we determine that this must have been the focus of the earthquake. This technique is called triangulation. This is the technique of finding the epicenter using the relative distances of 3 or more locations from the epicenter. Now, I'm sure most of you guys are familiar with using GPS. You might have, maybe your parents have it in their car, or you have it on your iPhone. The global positioning system uses satellites and uses a very similar idea that we just use to figure out where the location of an earthquake focus is.
GPS is more accurately defined as a navigational system that relies on satellite signals to show an object's location. Devices that use GPS work by receiving signals from special satellites that orbit the Earth twice a day at an altitude of about 13,000 miles. 1, the current time, and 2, where exactly above the Earth the satellite is at that time. GPS receivers use this information to do a special calculation called triangulation. The receivers compare the time that the signal was sent from the satellite with the time that the signal was received. The difference in time indicates the distance between the receiver and the satellite. A GPS receiver needs to get signals from 3 satellites to calculate latitude and longitude. If it gets a signal from 4 satellites, it can also calculate altitude.
All right, now we know how to locate the focus of an earthquake. What are a few other characteristics or some other events that could happen due to earthquakes? First one is liquefaction landslides. Now, these are pretty scary. So the energy from the earthquake can actually turn the ground, which we normally think of as very solid and stable, into a substance kind of like a liquid, and we can get landslides, bad mudslides, etc. A lot of times these happen after volcanoes, but they can also happen after earthquakes as well. Another possible effect, if the earthquake happens under the ocean, you might get a tsunami. Sometimes people would call it a tidal wave. Tsunami, very, very scary and often causes quite a bit of destruction.
高台に上がっていく道路があるわけですね、はい、そしてこれ津波が襲ったのはだいたい揺れてから何分後ぐらいですか
？30分はかかっていないかな。
30分かかっていない、だいたい3時10分前後、はい、この雪崩海水がこう入ってきましたけれども、この時の感じというのはどういう感じなんでしょうか？
ものすごい、音と組織というか上がりましてですね、はい、中には車の中に取り残されたまま流された、釜石駅前では腰のあたりまで、
腰のあたり、
しばらく浸水していました。
はい、街がまさに津波に飲み込まれていく様子、柳田記者もこれレポートしていますけれども、はい、これ高さでいうと建物の何階ぐらいまで来てますか？
まあ水は来ましたけどガラスは割れてない状況で。
じゃあ2階の上ぐらいまでということですから、はい、まあ普通の感覚で計算もう降りようにも降りられなくなった方ですね、はい、この高台に上がった方というのはこの後決められた避難所の方に。
Well, that's all we have for you today. Hopefully you learned something, and we'll see you next time. See ya!